So again, that's just what it is. That's just the definition of what a rational expression is. That's all. Okay, now not only that, here are some examples, that is, I meant to say. Here are some examples. 1 over x, that's a rational expression. Remember, a constant alone is a polynomial. We also have 1 over x squared minus 1. That's another example. We have another one over here. X squared plus 4 over x to the 5th plus 3x to the 4th minus 2. So we have a few different examples of rational expressions. In fact, just like any integer itself is a rational number, the same thing with rational expressions. Any polynomial itself is a rational expression, because you could think of the polynomial as the polynomial over 1. Same thing. So technically, we have seen these before, in fact, although I didn't call them rational expressions until now. I mean, again, you do go a lot more into these and consider what are called rational functions later on in other math courses. For instance, I'm not going to actually consider a rational function, and I'm not going to go through how to graph it. The graph it takes, well, it's not terrible, but it takes a little bit of work. But there's other things I want to cover first. Okay, so this is what a rational expression is. Now, we have seen the concept of domain, with functions, and I think with equations, actually, if I remember correctly. We also have this concept of the domain of a rational expression. Namely, the domain of a rational expression, we might have seen this actually before, but it's just all the numbers except those that make the denominator 0. So in other words, it's all x such that q of x is not 0. Because you never divide by 0. Now, how do we actually find the domain? Well, it's a lot easier to work with with equality than with an inequality. So generally what we like to do is first, we determine the solutions of this equation. That is, we find all x such that q of x is 0. And the domain is everything else. So essentially here, you're looking for the numbers that are not in the domain. And everything else then must be in the domain. That's all we're doing. That's all we're doing. Okay, so in other words, we're going to solve this equation, where q is a polynomial. So we are going to use stuff that we've seen before, like factoring, polynomial, synthetic division, we're going to use the quadratic formula, things like that will come into play, as you could probably expect. So here's a quick example. We want to find the domain of this rational expression. Okay, well, here it's actually a little bit easier. Remember, we don't care about the numerator, right? Here, when we're looking for the domain, we don't really take the numerator into consideration, so to say. We're focusing only on the denominator. Same thing here. Not only that, it's a little bit easier here because this is already factored. Remember, if you have a product equal to 0, then at least one of the factors has to be 0. Really, from there, what we do to solve this kind of equation is we set each factor equal to 0 and solve. Looking for all possible x that make this equation true. So we set each factor equal to 0, which really gives us an equation, and we solve it. I mean, x equals 0, well, that's a solution right away, right? So we know 0 is a solution to this equation. Okay, what about these two? Well, for x minus 2 equal to 0, again, you just solve for x. We're using stuff that we learned earlier in the course. That's all we're doing. So in other words, here, what we're doing is we're going to solve this equation for x, so we're going to isolate x. So let's get the 2 on the other side. So we add 2 to both sides, get x equals 2, as you can see. Here, same idea. We have x plus 3 equal to 0. We want to get x all alone. We subtract 3 from each side, get x equals -3. That's what we get. Okay. So the domain then would be everything except 0, 2, and -3, right? Those are the solutions to this. The domain is everything else, basically. So the domain is all numbers except 0, 2, and -3. I mean, for this kind of question also, I mean, there are mathematical ways to write it, math notation, that is. But if you just write something like this on an exam or quiz or whatever, with me at least, that's fine. There's a lot more fancy notation the book does, but the time consideration, I'm not going into that. Okay. Are there any questions about this example? Remember, I can't see the chat, so if you have a question, use the hand raise feature. Okay. Here's another one. So here we want to know what the domain of this is. Right? Okay. Well, how do we do that? We have to determine when the denominator is 0. That's what we have to do. So we want to solve this equation, in other words. Now, in this kind of example, what I would do, unless told otherwise, I would try to use the quadratic formula. Now, here, remember, in the quadratic formula, I have it written here, where a is the leading coefficient, so 3. B is the coefficient of x, which is 5. C is the constant term. Before I had this as -11, but I want it to be positive. That's why the positive symbol's here. I don't have to write a positive symbol here normally, but I'm just explaining why this is here. So because of that, we use the quadratic formula, and we get -5, right? Plus or minus, that's what this means, plus or minus, the square root of 5 squared minus 4 times 3 times 11, all over 2 times 3. From there, we get this. Now, just doing some calculation. And one step further, we get this. Notice we're taking the square root of -107. Well, you can't take the square root of a negative number, right? That is, the square root of a negative number here, right? It's not a real number. So the domain, so in other words, the denominator is never 0, meaning this equation has no solutions. And why is that? Square root of a negative is not a real number. So what does that tell us? This has no solutions. So the domain is everything. The domain is all real numbers, which I wrote as an interval. So we use the quadratic formula here. Here you can see an advantage of the quadratic formula, right? Because if you tried factoring this thing, then that doesn't look fun. Doesn't look pretty to do. In fact, it looks like you're not able to factor it, but that's a different story. All right, any questions on this? Okay. Now, I know we didn't do it in this class, but we have heard of writing a fraction in reduced form, or lowest terms, excuse me, a fraction of integers, that is. You could do something similar with rational expressions. except we say it's simplified instead of saying it's in lowest terms. So in other words, we say a rational expression is simplified if the numerator and denominator, right, if they have no common factors besides 1 and negative 1. I mean, 1 and negative 1, those could be factors of polynomials. And you know, you can't, they're always going to be factors of any two polynomials. You just can't get around it. You can't. But if those are the only two, then we say it's simplified. You know, again, that's just a definition here.